Welcome everyone to 11.10 Taylor and Maclaurin series. Now I'm back here in 11.9 because I have a little bit of a story to tell before we get to 11.10. So in 11.9, one of the main objectives was to understand how functions can be represented as power series. And we did an okay job with this. So we had this nice theorem. We learned how to represent things that look like 1 over 1 minus x as a nice power series. And then with examples, we learned how to expand this, right? So we got a lot of linear functions. In fact, in this first example, 11.9.2, we have 1 over 1 minus 3x squared. We have more complicated stuff here in the next example, 11.9.3. We learned about how can I represent things like natural logs or tangent inverse, all these things as power series. But there are a lot of functions that we left out, things like e to the x. For instance, how do we represent this as a power series? Well, Taylor and Maclaurin series takes a good stab at solving this problem, representing the kind of a lot of other functions as power series. So in 11.10, we're going to go ahead and define and compute Taylor and Maclaurin series. We're going to define and compute Taylor and Maclaurin polynomials, which turns out are interesting in their own right. We'll recognize what these polynomials are actually telling us, and then finally we'll define and calculate some remainders. So let's go ahead and consider this function 1 over x, and we want polynomials that approximate this function at a equals 1. So I've went ahead and I draw a dot on all of these pictures. So the best 0-degree polynomial, which we'll call t sub 0 of x, basically all we can do is just agree with f at 1. So here, well, 1 over 1 is 1, so it's a nice horizontal line, right? Because with a degree 0 polynomial, you don't get any variable, and it's just the equation y equals 1. So t sub 0 equals 1, no matter what x value it is. Okay, moving on, the best degree 1 polynomial, which we'll call this t sub 1 of x, can not only agree with f at 1, but it can also have the same slope. Okay, so maybe the first step, let's go ahead and figure out what is the slope of our function at 1. So we're going to go ahead and take the derivative. I get my negative 1 over x squared, just using the power rule here. And then if I go ahead and I plug in 1 for x, we're going to see that the slope at this point should be negative 1. Okay, so a polynomial that has slope negative 1 and intercept, well, we don't really have the intercept. All we know is that it hits this point 1, 1. So we can use point slope form and we get the equation 1 plus negative 1 times x minus 1. Now, we should remember this, right? So the line of best fit in some sense in Calc 1 was called the tangent line. So this was a linear function that well approximates the function around this value, in our case 1. So how about if we expand this even farther though and we go to a degree 2 polynomial? So we're going to call this t sub 2, and it can agree with f at 1, have the same slope, but also have the same concavity. So this concavity has something to do with degree 2, right? So a second derivative. So let's go ahead and take a second derivative now, again using the power rule from our first derivative. And we're going to get negative 1 times negative 2 over x cubed. Evaluate at 1. And this is going to give us 2. Okay, so a second degree polynomial, aka a quadratic, where we're going to have the same stuff as our first degree polynomial, so 1, and then we have our negative 1 times x minus 1. And then we're going to go ahead and we're going to add in our quadratic term. So this is going to be something like 2, right, because that's the concavity here, times x minus 1 quantity squared. Again, we're kind of all centered around this 1 value. But when I take the derivative, we'll see that something doesn't quite work out. So I take the derivative here. Let's see, I get negative 1 plus 4 x minus 1. So at the face of this doesn't seem super horrible. If I plugged in t equals 1, I would indeed get the slope is negative 1. Perfect. But now when I take the second derivative, we actually see that we get out 4, right? But we wanted 2, right? The second derivative at 1 was supposed to be 2, and I got 4. So what we want to do here is that we want to go ahead and divide by 2, so that way it kind of cancels when we take the derivative and this 2 comes down. So instead of 2, I'm going to put just 2 divided by 2, which I know is the same thing as 1, but kind of it's important to realize how we get there, right? So this is 2 divided by 2. Okay, now let's go ahead and double check. When I take the first derivative, I would get -1 plus 2x minus 1, and when I take the second derivative, I get 2. So we can see that the first derivative checks out and the second derivative checks out. So we've kind of captured not only the function's value, but we've also gotten its slope and we've gotten its concavity. Now, if we were to draw this best approximation for a quadratic, it would look something like this. Not a great approximation, but okay. And in fact, why don't we do it right now with our graph here? We can see I've done a few steps. I have the tangent line, but I also have the quadratic and even a 7th degree polynomial here. So right now I'm just looking at 1 over x. That's all I have graphed here. And let's go ahead and graph the linear and the quadratic. So this t sub 1 and t sub 2. Okay. Okay, so here they are. The red one is, of course, our line of best fit. That's our tangent line. And then here's our quadratic of best fit in some sense, right? Our t sub 2. So we can see it does a good job around 1, but then as it gets farther and farther away from 1, it starts to do a worse and worse job. And hopefully we can see that the quadratic does a better job than the line. Again, not great, but a better job. It stays closer to the function for longer. Now let's go ahead and I have graphed I have a cubic, right? So this one's in yellow now. We can see how well the cubic does. So again, yellow, it looks like this is even closer to the white line. Remember, the white line's the actual function. It stays closer for longer. So if I had to hypothesize something, I'd say a higher degree polynomial seems to approximate the function better for longer. Okay, so I have one more. I have the 7th degree. This would be t sub 7. Now I'm just claiming that it's t sub 7. I haven't, proven this in any way. But now look how good this does. You can see kind of between 0 and 1, it does a pretty good job, and between 1 and 2, it does a pretty good job. Now after 2, it starts to deviate quite a bit. You could think about this as an idea of a radius of convergence, right, that we know from before. Now radius of convergence, you would hypothesize for this would be something like 1, because once you get farther than distance 1 away from this center point, which is a equals 1, once you get farther than distance 1 away, kind of all of these polynomials start doing a pretty bad job. And so you would expect maybe the series would also do a relatively bad job. But we'll get into proving this later. So, a theorem now. If f has a power series representation or expansion at A, that is, if we can express f as the sum from n equals 0 to infinity of some constants, c sub n, times x minus a raised to the n, where x minus a, right, the distance from x to a is less than r, some radius of convergence, then the coefficients are given by a formula. And those are this c sub n is equal to f to the n, right? This is an nth derivative of f. That's why they have these parentheses here. The nth derivative of f evaluated at a divided by n factorial. So let's go ahead back here and verify this formula, at least for the example that we're given. So degree 1 polynomial, if I wanted to calculate out c sub 1 here, for instance, well, we hope that it's -1, right? So c sub 1 is supposed to be equal to the first derivative evaluated at a divided by n factorial. So there's 1 factorial, and indeed we can see -1 divided by 1 factorial is indeed -1. Now c sub 2, take a second derivative evaluated at 1 divided by 2 factorial. So this is essentially why we had to divide by 2 here. And you can see now how this expands as I would to go to calculate out a c sub 3 or c sub 4 or in general c sub n, right? You'd have to divide by higher and higher factorials. Okay, now if f has a power series expansion at a, then the following, it must be of this form. So now I'm just going to expand this out, kind of plugging in my c sub n's. So the sum from n equals 0 to infinity of the nth derivative of f evaluated at a divided by n factorial times x minus a to the nth power. Again, this is just plugging in my coefficient formula into my power series equation. So writing this all out, f of a plus f prime of a divided by 1 factorial times x minus a plus f double prime, second derivative, evaluated at a divided by 2 factorial times x minus a squared, and so on and so on and so on. This is called the Taylor series of a function at a, or about a, or centered at a. And we have a special case, right? So for when a equals 0, we can kind of simplify things. It looks a little nicer. So the Taylor series becomes the sum from n equals 0 to infinity of the nth derivative of f evaluated at not a now, but 0, right? Divided by n factorial times x to the n, right? So this is f of 0 plus f prime at 0 divided by 1 factorial times x. Again, we could simplify this down. Plus the second derivative evaluated at 0 divided by 2 factorial times x squared, plus so on and so forth. This case arises quite frequently. We give it a special name. It's called a Maclaurin series. So that's Taylor and Maclaurin series. Okay, so let's go ahead and try to apply some of this stuff. We're going to try to find a second degree Maclaurin polynomial for f of x equals the square root of x plus 1. So basically we're going to stop when we hit a degree 2 polynomial. We're not going to figure out the infinite series, not yet. So again, when you see this word Maclaurin, this automatically means a equals 0. So this tells you some stuff. So we really need to figure out c sub 0, c sub 1, and c sub 2, right? We need to figure out these 3 coefficients. And well, according to our formula that we have, we know how to evaluate these things, right? And once we have them, then we can put them together and we get a quadratic, right? C sub 0 plus c sub 1 times x plus c sub 2 times x squared. So, okay, well, c sub 0, that's just supposed to be f evaluated at 0. C sub 1 is supposed to be f prime at 0, technically divided by 1 factorial, which is really the same thing as just f prime, right? And then finally, c sub 2, this is f double prime at 0, second derivative, divided by 2 factorial. So that's f double prime at 0 divided by 2. So let's try to figure out what these things are. So if I was to plug in 0 into my function, I'd get the square root of 1. Square root of 1 is just 1. Okay, how about a first derivative? If I was to take a first derivative, let's see, power rule. The 1/2 would come down. I'd have times x plus 1 raised to the negative 1/2. And then chain rule, technically multiplied by 1 in this case. So if I plug in 0 now, let's see, I'd have 1/2 times 1 to the negative 1/2, which is just going to be 1. So therefore, we get 1/2 here. And then finally, c sub 2. Well, c sub 2, when I go ahead and take another derivative, we get negative 1/4 times x plus 1 raised to the negative 3/2. Go ahead and plug in 0, and I get negative 1/4. And I need to divide that by 2 to give me my negative 1/8. All right, combo it all together, and we get our final answer, right? So we have 1 plus 1/2 x minus 1/8 x squared. And that is our final answer. That's the second degree Maclaurin polynomial for our function. So now let me go ahead and graph it really quick and show you that it does a decent job approximating a function at least around a equals 0. So the first thing I'm going to go ahead and graph is the function itself. That's going to be the white function. And then I'm going to graph our second degree Maclaurin polynomial. It's a nice quadratic. And hopefully it approximates the function well at least around 0. All right, so I'm going to go ahead and hit graph. And let's see. There you go. Let me expand this a little bit. So around 0, you can see that this quadratic does a pretty good job of approximating our function. And as you get farther and farther away from 0, it does a worse and worse job. Okay, so we won't graph all of these all the time, but I insist on graphing the first couple just so we can figure out what exactly we're finding, right? Because this is complicated. All right, and that's just about it here in 11.10, at least for our first video. We have a lot of concepts in this video, so in the next couple videos, we're going to do some examples. All right, I'll see you shortly.